Chapter 4 of Class 11 Physics, Laws of Motion, Part 4. I have completed the Newton's laws and a part of friction in my previous videos. Now I will continue from where I left off in my previous videos. I think I stopped here at example 4.8. See figure 4.11. A mass of 4 kg rests on a horizontal plane. The plane is gradually inclined until at an angle theta equals 150, not 150, 15 degree with the horizontal. The mass just begins to slide. What is the coefficient of static friction between the block and the surface? The mass, basically the block is kept like this, but until this angle becomes 15 degree, the block will not move. But at the time when this angle is 15 degree, then this block will start to move. That is due to the mg sine theta component. So we can say that mg sine 15 degree, which is equals to the maximum frictional force Fs max. So based on this, they're asking the coefficient of static friction between the block and the surface. Mg sine 15. Sine 15 is a standard value which you should know. Mu s times normal force is basically normal force is equal to mg cos 15, this one. So mg cos 15 degree, mg cancel, so we don't need the mass of the block basically if you want to find the static friction. Then sine 15 by cos 15, which is equals to tan 15 degree, equals to mu s. Yeah, that's what we got here. The forces acting on the block mass m at rest on an inclined plane are the weight mg acting vertically downwards, the normal force n on the plane of the block, and 3, the static friction force Fs opposing the impending motion. In equilibrium, resultant of these forces must be 0, resolving the weight mg along the two directions shown in the diagram, of course, here. And if we want, before seeing the answer, the main points in the question are, they gave the plane, this is the main point, theta equals 15 degree, inclined is the main point, and the most important is mass just begins to slide. These are the important points. I will highlight them with another color. Theta equals 15 degree. It's not visible, I guess, right? Theta equals 15. The mass just begins to slide, and coefficient of static friction. These are the main points of the question. And drawing a free body diagram is also very helpful when we are solving these kind of questions. So let's continue anyways. Mg sine theta equals static friction. Mg cos theta equals the normal reaction. As theta increases, the self-adjusting force increases as well until theta equals theta maximum, which is 15 degree, where the gradual inclination stopped. And Fs also, the static frictional force, also reaches an maximum value, which is Fs maximum, which is equals to mu s times n. Therefore, basically what I solved down below, tan theta max equals mu s, or theta max equals tan inverse of mu s. When theta becomes just a little more than theta max, there is a small net force on the block and it may begin to slide. Note that theta max depends not only on the coefficient of static friction. Basically, this theta, this um the static friction only depends on the theta maximum theta value, and it is independent of the mass of the block. No matter if the mass of the block was like 5 kg, 500 kg, or anything like that, it will always be same. That is, I'm talking about coefficient of static friction. For theta max, which is equal to 15 degree, mu s equals tan 15 degree, the value is approximately 0.27. Now let's see the next question. What is the acceleration of the block and trolley system shown in figure 4.12, where the coefficient of kinetic friction between the trolley and the surface is 0.04? What is the tension in the string? Neglect the mass of the string and take g equals 10 power minus 10 meter per second square, not 10 power. Okay, let's mark the important points of the question. The questions here is, what is the acceleration of the block and trolley system? Coefficient of kinetic friction is 0.04. Tension in the string. These are the main important points. Acceleration of the block and the trolley system basically. And what is the, if the coefficient of static friction is 0.04, they give value of coefficient of kinetic friction, not static friction, kinetic friction, and tension in the string. They're asking two things, acceleration and tension. And based on the diagram, if we see, they gave the mass of the block to be around 20 kg and the mass of this block to be this mass of this block to be 3 kg. So the downward force is 30 Newton, which is given here, 30 Newton. And since if the first thing, if you want to calculate is a tension, the tension will be also 30 newtons. The tension as well is 30 newtons, obviously. Now the second thing they asked, acceleration. Acceleration, if you want to calculate, we know that here also the force is 30 newtons. So, and 30 newton is the force, and frictional force Fk, which is equals to mu k times n. The n is normal force is 200 Newton, which is because it's a 20 kg block. So 200 times 0.04 equals Fk. If we calculate it, basically, they gave that tension equals 30 Newton. The block moving like this is a block of 20 kgs. This is the surface. This is the pulley. This is the weight of 2 kg, connection here. Mass of 3 kg, tension like this, and here tension like this. Wait, no, the tension is not like that, but like this. Fine, I guess. It is always in the opposite direction of the force. The force is in this direction, the force is in this direction. Fine, leave it be. Leave the tension be. Okay. The force is transmitted throughout a massless string, 30 Newton here. Tension also 30 Newton. Here as well, the force this side is 30 Newton. Then the normal force on the block is force equals mass times acceleration, which is 200 newtons. Normal force is 200 Newton. And so we can calculate F kinetic for frictional force. Kinetic frictional force is mu k times normal force, is equals to 0.04. They gave the value of mu k, coefficient of kinetic friction, times 200, which we can write as 4 times 2, which is 8. 8 Newton is the frictional force. So if we want to calculate the acceleration, force equals mass times acceleration. Total force is equals to the actual force, which is 30 newtons, minus 8 newtons, the frictional force, which is opposing the moment, is equals to mass of the block. They gave it to be 20 kg. 20 kg times acceleration. So acceleration equals 22 by 20. 2 11s are, 2 10s are, and it is 1.1 meter per second square. 1.1 meter per second square. I think there is answer here. Is it correct? Wait. Okay, let's see how they solved the question. As a string is inextensible and the pulley is smooth, the 3 kg block and a 20 kg trolley both have the same magnitude of acceleration. Applying second law of motion to of the block, 30 minus tension equals 3 kg times A. Here, since the string is inextensible, we can say both acceleration is same. Okay, that is what they are doing here. Both acceleration is same. This acceleration is mass into acceleration. Force is 30 Newton due to gravity, which is mass times acceleration into 10. Wait, 30 minus t, which is equals to 3 into 10, or 3 times, wait, acceleration is not the same. Since there is an inextensible string, apply the second law of motion to the trolley. Tension total force is equals to 20A. Okay. And this one, we will get it to be around 8 Newton. So T minus 8, which is equal to 20A. Both equations, we take linear equations, I guess. These give the acceleration to be 0.96 meter per second square and tension to be 27.1 Newton. Fine, I guess. I'm not sure where I did wrong, but that's okay too. Okay, let's go to the next main topic, that is we studied about static and kinetic frictions. Now let's go to rolling friction. A body like a ring or a sphere rolling without slipping over a horizontal plane will suffer no friction. In principle, basically, if a body that is like a ring or a ball, which is a sphere, is rolling down, maybe downhill, without slipping over, without any kind of sliding motion, then there is no friction at all. At every instant, there is just one point of contact between the body and the plane, and this point has no motion relative to the plane. Basically, at every instinct, not instinct, but every instant, there is just one point of contact between the body and the plane, and this point has no motion relative to the plane. Okay, basically, they're talking about here. Let's draw a diagram. Let's assume this is a downhill. This is a ball that is rolling down. At this point, at this instant, only this point is in contact with the ground here, and when this goes forward, one more point. In this case also, only one point is in contact with the ground. Okay, that's what they're saying here. A body like a ring or a sphere rolling without slipping over a horizontal plane will suffer no friction in principle. At every instant, there is just one point of contact between the body and the plane, and this point has no motion relative to the plane. When at this instant we take this point, the point in contact with the ground has no relative motion with the ground, thereby no friction. There is no sliding, right? So there is no friction as well. In this ideal situation, kinetic or static friction is zero and the body should continue to roll with constant velocity. But in a very ideal kind of situation, in an ideal world, because in every instinct, not instant, every instant the ball is in contact, but it is not in relative motion with the ground. So in such a case, in an ideal situation, the ball should continue rolling down or continue rolling, not down. Even in a horizontal plane, you just continue rolling down, not down, just continue rolling. That is because there will be no friction. But in ideal situations, there are three reasons that doesn't happen. There can be more than three, but I think there are three, which I noticed three, which is one, there is, even though it is possible that there can be no, there are moments where static and in reality, in, let's say, ideal situation first. Ideal situation, the ball should experience no static or kinetic friction and should continue rolling. But in In reality, such there will always be minute amounts of static and kinetic frictions in rolling friction as well. And we can also, in reality, there is will be air resistance. That is also one of the reason. Air resistance, gravitational pull, when it is going up, the gravity will reduce the velocity of the ball, so that can also stop the motion of the ball. Okay, let's read. That is the reason. These are the reasons why it is not ideally possible when we roll a ball, it will not continue to stay rolling, it will comes to a stop. A body like a ring or a spear, without a spear rolling, without slipping over, that is no sliding motion here over a horizontal plane, will suffer. And specifically mentioning, a horizontal plane will suffer no friction, and in principle at every instant there is just one point of contact between the body and the plane, and this point has no motion relative to the plane. And in this ideal situation, kinetic or static friction is zero, and the body would continue to roll down with constant velocity. We know in practice this will not happen, and some resistance to motion, rolling friction, does occur. That is, to keep the body rolling, some applied force is needed. For the same weight, rolling friction is much smaller, even by 2 or 3 orders of magnitude, than static or sliding friction. Basically, they gave two information. No wait, three info. No wait. The first information they gave is that it is not ideally possible because there will always also be a rolling friction in practice. There is another kind of friction other than kinetic and static friction, that is rolling friction, that will be coming up, that is getting applied here. And we also need force. We need to continuously apply a force on the body to keep it moving or keep it rolling. And the third information is, but the rolling friction rolling is less than kinetic, less than static. This is a order of 2 to 3 orders of magnitude. It can be much smaller than these both, even in like where rolling friction, if it is 1, the kinetic friction will be 3 or 4, or even 2 or 3, like that. It will be much smaller. Rolling friction will be much smaller than kinetic and static frictions. That is what they mean here. Let's see some ways of reducing friction here. The diagram here, some ways of reducing friction. A ball bearing placed between moving parts of a machine. This is a ball bearing. This will help reduce the friction. Compressed cushion of air between the surfaces of a relative motion. Air cushion, plastic disc with a hole, and an inflated balloon. Okay, let's observe this more. Read first. This is the reason, like, why, because we know that rolling friction is much lower than kinetic and static friction. This is the reason why discovery of wheel has been a major milestone in human history. Rolling friction again has a complex origin, though somewhat different from that of static and sliding friction. During rolling, the surfaces in contact get momentarily deformed a little, and this results in a finite area, not a point, of the body being in contact with the surface. The net effect is that the component of the contact force parallel to the surface opposes motion. They are saying that this rolling friction, we theoretically, if we say it should, the ball, like the ball should continue rolling for no matter how long the distance, but that is not happening. Why that is not happening is because, why this rolling friction is coming into action is because we only consider rolling friction when only one point of the body is in contact with the ground. But in real situations, if this is the ground, there will always be, due to a little deformation of the ball, that doesn't look like a ball, but let's assume it is a deformed a little. In such a case, this is a finite area here. It is a finite area is under contact with the surface or with the ground. So sliding friction also takes place, a little amount of sliding friction. Due to such a reason, another name for it is called as rolling friction. The rolling friction is only truly ideal only when a single point of the body comes into contact with the surface. What is that? That is almost very hard to achieve. We often regard friction as something undesirable. Normally, we regard friction as something undesirable because we see a friction as an enemy. But friction is not an enemy. In many situations, like in a machine, where we consider friction as an enemy is because, like in a machine with different moving parts, friction does have a negative role. It opposes relative motion and thereby dissipates power in the form of heat. Heat is produced. Lubrication are a way of reducing kinetic friction in the machine. Another way is to use ball bearings between two moving parts of a machine. Since the rolling friction between the ball bearings and the surfaces in contact is very small, power dissipation is reduced. A thin cushion of air maintained between solid surfaces in relative motion is another effective way of reducing friction. Okay, this is basically not a machine where we see such a thing. This is basically a home toy. They described a toy here, which is kind of a science experiment as well. When we take a plastic disc with a hole, let's take a donut like plastic disc. It should not be, the hole should not be too big, but something like this. And where we inject the balloon, we fill the balloon and we inflate the balloon. And once we release this on the floor, there will be a thin air cushion formed between the, normally if the surfaces of the plate and the floor are like this, but when there is a balloon blowing the air, the surfaces of the earth and the surface of the plate will be like this, and in between this will be air. This is like a hovercraft. It's not completely a hovercraft, but it is similar to a hovercraft. It is, that is, if you know what a hovercraft is. Basically, our hovercraft is basically like this. It is hovering. It's not completely flying. It is above the ground, hovering over the ground. In many practical situations, however, friction is critically needed. Applications of friction here, or uses of friction, kinetic friction that dissipates power is nevertheless important for quickly stopping relative motion. Basically, let's assume uh, a machine is spinning. Like there is a spinning part of a specific machine. Let's assume that at the time of grinding or any kind of working of that machine, we turn the machine on and the machine starts spinning. But after some time, we need to stop the machine. We need to stop the machine if there is no kinetic friction or any kind of friction acting on that machine. Even if we turn off the switch of the machine will continue to go, will continue to work, and we need to apply an external force to stop the machine. But because there is kinetic friction, we don't need to apply that. The kinetic friction will do that work for us. It is made use of by brakes in machines and automobiles. If there is no friction between the road and the tires, there used to be no kind of brakes and all. Because if there is no friction at all, even if we apply brakes and the tire is stopped, the tires spinning of the tires is stopped, then since there is no friction, the car will continue to slide down or slide and crash. Similarly, static friction is important in daily life. We are able to walk because of this static friction, and static friction is also very important. We are able to walk on the floor because of static friction. We are basically, what is walking? We are pushing the ground backwards to move forward. So if there is no friction, we can't push the earth backward, so even we can't move forward. It is impossible for a car to move on a very slippery road. On an ordinary road, the friction between the tires and the road provides a necessary external force to accelerate the car. Now let's go to the topic of friction is finished. Let's go to the next main topic, that is circular motion. We have seen in chapter 4 that acceleration of a body moving in a circular radius with uniform speed v is v square by r directed toward the center. According to the second law, the force F providing this acceleration is mv square by r. Basically, this is about centripetal acceleration or centripetal force, not acceleration, centripetal force here. This is the centripetal force. We have already seen that the acceleration of a body, chapter 4 is basically this chapter only, the laws of motion. The acceleration of a body moving in a circular radius, moving in a circular radius with a radius r with a uniform speed v is, they're talking about a uniform speed because we cannot say uniform velocity. In a circular motion, the velocity is not uniform, it is always changing. The magnitude of velocity will remain constant, but the direction of velocity will always keep changing. At one instant it will be one direction, at other instant it will be other direction. And the acceleration towards the center, when a particle is rotating in a circular motion with constant velocity, not velocity, speed, there is a centripetal acceleration, an acceleration towards the center of the circle, and this acceleration is the centripetal acceleration. And we know that force equals mass into acceleration. That is the second law of Newton. Based on this, we know acceleration is v square by r. This is the acceleration towards the center, v square by radius, and this acceleration, substitute in the second law's formula, force equals mass mv square by r, which is the centripetal force. A centripetal acceleration, the acceleration towards the center experienced by a particle moving in circular motion, and centripetal force, the force experienced by the particle moving towards the center of this circle when it's moving in a circular motion. Where m is the mass of the body, this force directed towards the center is called the centripetal force. For a stone rotated in a circle by a string, the centripetal force is provided by the tension in the string. Basically, if we take a string, there is a diagram here. When we are rotating like this, when we tie a stone to a string and rotate it like this, the centripetal acceleration or centripetal force is the same force that the tension in the spring. Basically, the centripetal force is the tension in that case. That is what they mean by that. The centripetal force is provided by the tension in the string. The centripetal force for motion of a planet around the sun is the gravitational force on the planet due to the sun. Basically, when the planets are revolving around the sun, the centripetal force on the planets due to that rotation or revolution is provided by the gravitational force on the planet that is provided by the sun. And for a car taking a circular turn on a horizontal road, the centripetal force is the force of friction, where the friction will provide the force. If it is not provided by friction, the car would slide, and get crashed during taking a turn. The circular motion of a car on a flat and banked road give interesting application of the laws of motion. But here, we saw three cases of centripetal acceleration, and it was only provided where, in case of the first case, tying a stone to a string, it is provided by the string when we are rotating the stone, and in case of the planets, provided by the gravitational force of the sun, and in case of the car, it is provided by the friction. But what if it was only a system? It was a universe where, or a system where there are no other external forces acting on the system, and it is moving, and only one kind of force is acting on it, that is making it to go in circular direction. Then what would be the centripetal force provided by? Let's see that. If in a system where a particle is only under a single force, which is making the particle to undergo circular motion with constant speed, then what is the centripetal acceleration and force centripetal provided by? A particle is acted upon by a single force, and single force must be directed towards the center of the circle at all times. the net force is not zero. It causes continuous acceleration, change in direction. String is the only force pulling inward. The tension is the centripetal force. Only force is gravity. Okay, that only force is providing the centripetal force as well. Okay, if there was no string itself, in case of a rotating stone tied to a string, if there was no string itself, then of course there would have been no, like there was no circular motion itself, right? If there was no string pulling the stone to the center, there would have been no circular motion itself. And even in the another case um, where where in case of gravity, if there was no gravity, then the planets would not have revolved around the sun. So it is actually the centripetal force that is actually causing the circular. We can understand it in a different way, that the centripetal force is the one that is causing the circular motion and not the other way around. So is the centripetal force the one causing circular motion and not circular motion, creating centripetal force. Okay, yes, that is indeed the case. The circular motion doesn't provide a centripetal force, but a centripetal force is the one that causes a circular motion. This is better to understand it this way. But since we do not see the forces, we see that if it is moving in a circular path, we assume that it is there will be a centripetal force, because if there is a centripetal force only, the particle will go in a circular motion. But since we can't see force, we will assume that circular motion creates the, or if there is circular motion, then there will be a centripetal force. And in case of a car moving, if there was no friction, then the car wouldn't have taken the turn itself. It would have just gone straight if there was no static friction between the tires. Okay, then let's see the diagram first. Circular motion of a car on a level and banked roads. A is on a level road and B is in a banked road. Basically, when it is taking a turn like this. This is the curved road where this is the car. It is taking a curve like this, and when it is going a curve, it means there is some centripetal force acting on it, and it will act towards the center, and the friction is acting opposite to that. The friction is acting, and in this case, if we see in a banked road, let's leave this be for now. In case of a banked road, an angle theta, the n here normal force, and cos theta and n the main n, and this side towards the center is the centripetal acceleration. Okay, fine. The ones acting completely downwards are f sine theta and mg sine theta. the frictional force acts towards this direction. Okay, then one of the subtopics we are going to see is motion of a car on a level road. Three forces act on the car when it is moving on a level road. That is the weight of the car, normal reaction, and frictional force. As there is no acceleration in the vertical direction, that is forward up, like, okay, they are talking about in the y-axis there is no acceleration. The only acceleration is acceleration due to gravity. We can say normal force is equal to mg. The centripetal force required for circular motion is along the surface of the road and is provided by the component of contact force between the rod and the car tires along the surface. This by definition is a frictional force. Note that it is the static friction that provides the centripetal force. Centripetal acceleration, static friction opposes the impending motion of the car moving away from the circle. Basically, why we take, when the car is moving, why we take in static friction instead of kinetic friction is that the friction is acting in the direction where the car is not moving. The car is not drifting, so it is about to drift. If it was going to drift, if there was no friction. So in such a cases, there is impending motion of the, or impending drift of the car, like that. So we consider static friction here, and not either kinetic or rolling friction. And this is provided by the centripetal force is, okay, it is kind of confusing, but for the car to undergo circular motion, there must be a centripetal force, and this centripetal force is the friction of the car's tires, and this is acting towards the center, and it is equal to the centripetal force, which is mv square by r, which is less than or equal to mu s n, because friction is not always a maximum. Mu s n is the fs max value, but the centripetal force will be varying depending on the velocity of the car and other things, mass of the car, etc. So using equation 4.14 equation, yes, this equation, the static friction equation, the result is F equals mv square by r, which is less than equal to mu s n. V square, when we shift the mv that side, you will get v square is less than or equal to mu s rn by m, and we can take n by m, which is normal force per mass. We can write normal force, which is equal to mg by m, which is basically m, which is remaining is g. So that is why they wrote g here. G is the acceleration due to gravity, which is 10 meter per second square, and r is the radius of the entire circle. And when we want the v maximum, the maximum velocity where the centripetal force it will reach maximum, basically this is actually application. Okay, let's read first. I'll tell which is independent of the mass of the car. What is independent of the mass of the car? The velocity is independent of the mass of the car. This shows that for a given value of mu s and r, there is a maximum speed for a circular motion of the car possible, namely v max equals root mu s r g. What this means is, it's a point here, important points here to understand this statement is circular motion of the car possible independent of the mass of the car for value of r maximum speed of circular motion. Basically, if it exceeds this vmax value, the velocity of the car exceeds this V max value, there will be no circular motion. It will exceed the maximum frictional force possible, and the car will drift. It will drift, it will roll down, or it might crash. Anything might happen. So when we see boards, where the speed limit boards basically in the turnings and all, those are calculated based on this and are kept. So during turns we need to follow that, so that there is no drifts or there is no accidents. Motion of a car, and whatever we saw here, this mu srg or root mu srg is on a horizontal road. But what if it is a banked road? Motion on a car on a banked road, where here as well the components will be same, but wait, the main forces will be same, but in case of the components which we do not consider will be removed, and an angle is considered here. So okay, and normal force is also reduced because it is, wait, no, normal force, yes, it is a resolution of the mg component, mg sine theta. Fine, let's see. We can reduce the contribution of friction to the circular motion of the car if the road is banked. Since there is no acceleration along the vertical direction, the net force along the direction must be 0. Hence, n cos theta equals mg plus f sine theta. N cos theta, if we see the forces acting downward in the complete y direction, it is mg, which is always acting towards the center of the earth, which will always be perpendicular to the main x-axis. And the f sine theta, the frictional force acting this side, this way, and when we component, this will be the cos component, and this is a sine component, mg downwards, and n cos theta, when we resolve it into two components, n cos theta acts upwards, and both must be equal because there is no net acceleration of the body. The car is not going into the earth or flying up into the sky. So in such a case, we can say n cos theta equals mg plus f sine theta. That's what they wrote here. The centripetal force is provided by the horizontal component of n and f. So n sine theta plus f cos theta is equals to mv square by r. Basically, the forces acting on the towards the center of the circle are namely the, let's erase this once. The forces acting in this direction towards the center are f sine theta and n sine theta as well. N sine theta, this force, and f cos theta also acting towards the center of the circle. So centripetal force must be equal to the sum of n sine theta plus f cos theta, which is equals to mv square by r. And when we calculate, but friction is less than or equal to mu Sn, thus to obtain V max value we put friction equals mu Sn, then equations 4.19 and 4.19b become n cos theta equals mg plus mu Sn sine theta. Okay, this is along the vertical direction, where n cos theta equals mg plus f sine theta, and this is along the horizontal direction, which is acting towards the center, is equal to centripetal force. And when we substitute that frictional force is mu Sn in the first equation, f will become mu Sn. That is what we get here, n cos theta equals mg plus mu s times n sine theta. And in the second equation, n sine theta plus mu Sn cos theta, which is equal to mv square by r. And from this from the above equation, from here we obtain the normal value which is mg by cos theta minus mu s sin theta. Substituting the value of normal in equation 4.20b, you will get mg sin theta plus mu s cos theta by cos theta minus mu s sin theta is equals to mv square by r, and v max will become a root of rg mu s plus tan theta by 1 by mu s tan theta. Okay, fine, but okay, since we don't know the, but we do know the mg value, I mean n value, which is a component of mg, but mg's but there might have been a problem taking the theta factor. Maybe we need to take another angle to resolve this mg component. Maybe that is the reason they didn't take mg cos theta or sin theta for n value. Fine, okay, from theta values we will get this value. This is the final equation for Vmax on a banked road. The maximum speed you can go in a bank road to avoid drifting. And if we compare to the equations, if we compare the frictional force, or wait, here even mg can be included, maybe. Wait, when we resolve it in terms of like this, then maybe even the gravitational component can be used for, can be acting as the but it's not acting towards the center. Okay, it's completely perpendicular like this. It is not acting towards the center, it is acting downwards, so we not consider mg there. Fine, okay. Okay, let's continue. Okay, I was comparing which will have a more centripetal acceleration. It will, I believe it will be for B, where the Vmax value will be higher compared to A. That might be the case because here the forces, normal reaction force is also acting this way. Let's ask, in case of turning in a, not in a, but on a banked and horizontal road, which will have a higher velocity, higher maximum velocity value to keep the car in circular motion. Horizontal flat road, it is root m mu gr, and in case of the bank road, that is without friction, it is rg tan theta, and bank road with friction, final comparison, the maximum speed for banked, that is with friction, is higher than both of the above. This value will be higher than the both of the above values, that is with banked with no friction. And basically, if the car can turn without friction itself, we can indeed compare, we can say that banked with friction will allow more speed as well. Maybe that is the reason race tracks have banked roads. Comparing this equation with 4.18, which is root mu s gr, 4.18, it is here. It seems I have missed the 4.18. Ah, yes, this one. P max equals root mu s rg. Comparing both of them, we see that maximum possible speed of a car on a bank road is greater than that of a flat road. Mu s equals 0 in equation 4.21. When the static friction is 0, velocity is root rg tan theta. In this case, where mu s is 0, it is rg tan theta. At this speed, frictional force is not needed at all to provide the necessary centripetal force that is provided by the, if there is no frictional force, then who will provide the centripetal force for rotating? It will obviously be the normal reaction force. The normal reaction force acting this way, acting like this, will provide the needed centripetal force for the car to undergo a circular turn. Driving at this speed on a bank road will cause little wear and tear on the tires. The same equation also tells you that V is smaller than V naught, frictional force will be up the slope, and that a car can be parked only if tan theta is lesser than mu s. V is lesser than V naught, okay. Frictional force up the slope, and that a car can be parked only if tan theta is smaller than equal to mu s. Okay, basically from this equation, where tan theta, if it is, we can only park a car on a slope only when if the angle is the tan theta trigonometry, if we take with the theta is the angle or inclination of the slope, when we take it should be less than or equal to the coefficient of static friction. Only then when we park the car, it will stop moving. Example 4.10, a cyclist speeding at 18 km on a level road takes A sharp circular turn of radius 3 meter without reducing the speed. The coefficient of static friction between the tires and the road is 0.1. Well, a cyclist slip while taking the turn. Since it's a level road, we take root mu gr, root mu s gr, mu s gr, v max equals mu s gr. So mu s is 0.1 times 10, which is the gravitational force. R, they gave it to be 4 meters. Sharp circular, okay, it's 3 meters. 3 meters. In this case, we will get Vmax value to be around the root 3, which is 1.7 meter per second. They gave the speed to be 18 kilometer per hour. So when we multiply with 18 into, I think it was 5 by 18, then the velocity of the biker is 5 meter per second, whereas the max velocity is 1.7 meter per second. It exceeded almost 3 times, not yes, almost 3 times. So of course the biker will slip and fall and lose a teeth. Answer: on an unbanked road, frictional force alone can provide the centripetal force needed to keep the cyclist moving on a circular motion. Basically, this is also a point to be remembered, that is, on an unbanked road, the frictional force alone can provide the centripetal force. That is on a unbanked road. In a banked road, even the normal reaction will provide the centripetal force. That is why even without any frictional force, with a certain velocity, we can take a circular turn needed to keep the cyclist moving on a circular path without slipping. If the speed is too large, or if the turn is too sharp, too small of a radius, of both, the frictional force is not sufficient to provide the necessary centripetal force and the cyclist slips. The condition for the cyclist not to slip is v square should be equal to or less than mu srg, that is a root of mu srg, that is v should be less than or equal to root of mu srg, where r is the radius, which is 3 meter, g is 9.8 or approximately 10, mu s is 0.1, and mu srg, if we multiply all these things, we will get approximately 2.94. Velocity meter square, velocity for his velocity is 5 meter per second, that is v square equals 25 meter per second square, meter square per second square. The condition is not obeyed, the cyclist will slip while taking a circular turn. As I said, he will slip and fall and lose a teeth. A circular racetrack of radius 300 meters is banked at an angle of 15 degrees. The coefficient of friction between the wheels of a race car and the road is 0.2. What is optimum speed of the race car to avoid wear and tear on its tires, and maximum permissible speed to avoid slipping? Basically, they asked two things here: optimum speed points here, optimum speed of the race car, maximum permissible speed to avoid slipping. These are the question. A radius 300 meters. Important points of the question: banked at an angle of 15 degrees. Coefficient of friction between the wheels and race car is 0.2. It is a banked road, so we take this formula. On a banked road, the horizontal component of the normal force and the frictional force contribute to provide centripetal force to keep the car moving on a circular turn without slipping. At the optimum speed, the normal reactions component is enough to provide the needed centripetal force. What this optimum speed is basically, it is where mu s is 0 even without the frictional force. If there is frictional force, the tire will experience wear and tear, where the tire's grip will get flattened and reduced. It will experience wear and tear. If there is no need for friction itself to provide the turn on a banked road, and only the normal forces providing the centripetal force, then there is no wear and tear on the tires. Basically, when mu s is 0 we take, and the equation we will get is mu s equals root, not mu s, the velocity should be root of rg tan theta. That is what we calculate in the first option. And second option, the maximum permissible speed, that is this equation. Both equations, we substitute the value, we'll get the answer. Frictional force, and the frictional force is not needed. The optimal speed V naught or VO is given by equation 4.22, this equation. V naught equals Rg root Rg tan theta. Here R is 300, theta is 15 degree, G is 10 meter per second square or 9.8 meter per second square. V naught equals 28.1 meter per second, and this, if we multiply by 18 by 5, we will get the approximate kilometers per hour. The maximum, but this is where no friction force is required. But the maximum permissible speed Vmax, it is given by equation 4.21, and Vmax equals root of Rg mu s plus tan theta by whatever the equation is, and this will get to be around approximately 10 meter per second higher than the optimal velocity. Now it is time for the next topic, that is solving problems in mechanics. I'll be taking a 5-minute break. See you after the break. It seems it took a little more than 5 minutes. But then, now let's see to the next main topic, that is solving problems in mechanics. The three laws of motion that you have learned in this chapter are the foundation of mechanics. The three Newton's laws. The first law of inertia, the second law of change in momentum per unit time is the force, and the third law, which is the most famous one, and these are the most basic of the foundation of the mechanics. You should now be able to handle a large variety of problems in mechanics. A typical problem in mechanics usually does not merely involve a single body under action of given forces. More often, you will need to consider an assembly of different bodies exerting forces on each other. In real mechanics, we don't need to consider we like it's not so simple that we only consider the forces on a single body. We consider the forces on numerous bodies exerting forces on each other. Besides, each body in assembly experiences the force of gravity. When trying to solve a problem of this type, it is useful to remember the fact that we can choose any part of the assembly and apply the laws of motion to that part, provided we include all forms on the chosen part due to the remaining parts of the assembly. Basically, when we are trying to solve a problem of the mechanics type, it is useful to remember the fact that we can choose any part of the assembly and apply the laws of motion to that part to, to that part, provided we include all forces on the chosen part due to remaining parts of the assembly. Basically, we don't need to choose every single particle. We can only choose one single particle or part, and we can see the force and motion or behavior of that part, but we need to include the forces of all the other particles exerted on that single particle. That is important. We may call the chosen part of the assembly as a system and the remaining part of the assembly plus any other agencies of force as the environment or surrounding. We have followed the same method in solved examples to handle a typical problem in mechanics systematically. One should use the following steps. When we want to handle a problem in mechanics systematically or a traditional way, one should use the following step. We should follow the steps. First one, draw a diagram showing schematically the various parts of the assembly of the bodies, the links, the supports, etc. That is the first part. Choose a convenient part of the assembly as one system. We choose one part of the assembly as a system. Draw a separate diagram which shows the system and all forces on the system by the remaining part of the assembly. We should draw a separate diagram that shows the system and all the forces on the system by the remaining part of the assembly. Okay. Include also the forces on the system by other agencies. Do not include the forces on the environment by the system. A diagram of this type is known as the free body diagram. But this does not imply that the system is under consideration is without a net force. The system may have a force or may not have a net force. Here, let's read this third point again. The first point, we should draw a diagram. Second point, we should choose a part of that diagram and draw this part of the diagram separately. And the diagram shows system and all the forces. The system is a part of the diagram which you draw, which we call it as system, and this diagram will show all the forces on the system by the remaining part of the assembly. And we should include also the forces on the system by other agencies, but do not include the forces on the environment by the system. The thing we should not include is, we are only considering the system. We should consider the force applied by the environment on the system, but we should not include the forces by on the environment by the system. We should not include forces on the environment by the system. A diagram of this type is known as the free body diagram. Of course, it may not have force. In a free body diagram, include information about forces, their magnitudes and directions that are either given or you are sure of, the direction of tension in a string along its length. The rest should be treated as unknowns to be determined using the laws of motion. If necessary, follow the same procedure for another choice. Basically, the fourth point is we should represent everything, every kind of force, its direction and its magnitude in the diagram. And next is when the forces which we do not know, we find out. And the next point, fifth point, if necessary, follow the same procedure for we take another part of the system and follow the same procedure. In doing so, employ Newton's third law. That is, if in the free body diagram of A, the force on A due to B is shown as F, then in the free body diagram B, the force on B due to A should be shown as minus F. The following example illustrates the above procedure. Let's see the example. Let's see the figure 4.15. This is the figure 4.15. This seems to be a water here. Okay, free body diagram and 20 Newton downward force and the reaction force. Okay, this seems to be two blocks here. Let's see. Okay, 4.15, a wooden block. Okay, a wooden block of mass 2 kg rests on the soft horizontal floor. Important here is soft, that is important, horizontal floor. When an iron cylinder of mass 25 kg is placed on the top of the block, the floor yields steadily and the block and the cylinder together go down with an acceleration of 0.1 meter per second square. What is the action of the block on the floor? That is before and after the floor yields. Take G to be 10 meter per second square. Identify the action reaction pairs in the problem. Basically, when there is a soft floor, maybe it can be a floor like a trampoline we can take it, where there is a 2 kg block, it is horizontal completely, it is horizontal, it is in same kind of elevation. But when we place a cylinder of 25 kg above this wooden block, here at first the mass is 20 Newton, but when we place another block on this wooden block, we place a cylinder, then it will become 20 plus 250 kg, or I mean 25 kg, which is 250 Newton. 250 Newton plus 20 Newton is 270 Newton. The reaction force also changes. In this case, the soft ground, because it is soft, will bend in with a acceleration of 0.1 meter per second square. Now, what we should find is important in this question is a wooden block of mass 2 kg rests on the soft horizontal floor. Iron cylinder of mass 225 kg is placed on top of the block. The floor yields steadily with a speed of 0.1 meter per second. What is the action of the block on the floor? Action of the block on the floor before and after the floor yields. And identify the action reaction pairs in the problem. Okay, let's see the answer. A, the block is at rest on the floor. Its free body diagram shows two forces on the block. The force of gravitational attraction by the earth equal to 20 Newton and the normal force R on the block by the first law. The net force on the block must be 0, that is R20 using the third law of action of the block. The force exerted on the floor by the block is equal to 20 Newton and directed vertically downwards, because they're asking about the force experienced by the block, action of the block on the floor before and after floor yields. Before the floor yields, the block's reaction is, the block is exerting a 20 Newton force. Because the floor is not yielding, we know that it will also apply an equal 20 Newton force, that is a normal force, and this is directed vertically upwards. That is the case. Now the second, where we had a 25 kg cylinder, the system, block plus cylinder, accelerate downwards with 0.1 meter per second velocity, acceleration. The free body diagram of the system shows two forces on the system, the force of gravity due to earth and the normal force R dash by the floor. Note that the free body diagram of the system does not show internal forces between the block and the cylinder. Okay. Applying the second law of motion, 270 minus R dash, the change in force, which is equals to acceleration using force equals mass into acceleration formula. Mass is 27 kg, 2 kg plus 25 kg. Acceleration is 0.1 and the total force is the 270 Newton downward due to gravity, and R dash the normal force. So R dash, which is approximately 267.3 Newton. That is what they found out. And by the third law, the action of the system on the floor is equal to 267.3 Newton and vertically downward. And for the action reaction pairs, for A, system A, not system A, in the case A, where the free body diagram of the block is shown, where there is 20 Newton of force. One, the force of gravity 20 Newton on the block, and by the earth, the force of gravity on the earth by the block is equal to the 20 Newton directed upwards, not shown in the figure. Basically, in this case, the action reaction force is when the block is exerting a force of 20 Newton downward and the floor is also exerting an equal and opposite force of 20 Newton upward, the normal force. So the action reaction pairs here are the block and the floor. The force on the floor by the block, action. The force on the block by the floor is reaction. In the second case, where there is a cylinder, here as well it is the same. The force of gravity 270 Newton on the system by earth, say action. The force of system on earth by the system reaction equal to 270 Newton directed upwards. The force on the floor by the system, action. The force on the system by the floor. In addition, for B, the force on the block by the cylinder, the force on the cylinder by the block also constitute an all action reaction pair. In the first case, in this A case, in the first case, we see only one action reaction pair, that is the floor, and the second is the block. But in case of the third case, not the second case here, second case we see two action reaction pairs. One is the floor and the block. These are one action reaction pair. Then the cylinder and the block, these are also an action reaction pair, two action reaction pairs. Actually, when we talk about a block, it is not actually only the block and the floor, it is actually the whole system. 2 and 3 together constitute a system, and the action reaction pair is the whole system. The floor is exerting a force on the whole system and the whole system is exerting a force on the floor. The important thing to remember is that an action reaction pair consists of mutual forces which are always equal and opposite between two bodies. The two forces on the same body which happen to be equal and opposite can never constitute an action reaction pair. the force of gravity on the mass in A or B and the normal force on mass by the floor are not action-reaction pairs, these forces happen to be equal and opposite. For A, since the mass is at rest, they are not. So for case B, as seen already, the weight of the system is 270, or the normal force is 267.3. Let's read that again. The important thing to remember here is that an action reaction pair, this action reaction pair consists of mutual forces that are always equal and opposite between the two bodies. The forces on the same body, which happen to be equal and opposite, can never constitute an action reaction pair. Highlight here, everything is highlighted, but I will highlight it with a separate color so that it is easier to understand. Important thing to remember is that action reaction pair consists of mutual forces which are always unequal, and double highlight two bodies. It's not visible if I double highlight, I mean triple highlight actually. And the next is two forces on the same body which happen to be equal and opposite can never constitute an action reaction pair. These are the 2 points. Actually, I will do it with a different color. Two forces on the same body which happen to be equal and opposite can never constitute an action reaction pair. These are the two important points. The force of the gravity on mass in A first case or second case and the normal force on the mass by the floor are not action reaction pairs. These forces happen to be equal and opposite for A, but since the mass is at rest, but that is not the case for B. As seen already, the weight of system is 270 Newton, while the normal force is 267.3, which is not equal and opposite. The practice of drawing free body diagrams is of great help in solving mechanics. It allows you to clearly define your system and consider all forces on the system due to objects that are not part of the system itself. A number of exercises in this and subsequent chapters will help you cultivate this practice. With that, we have completed the normal topics. Let's see the summary. It's around 2 pages. Aristotle's view that a force is necessary to keep a body in uniform motion is wrong. Of course, this is Aristotle's fallacy. A force is necessary in practice to counter the opposing force of friction. That is the true modern physics view. This is the Galileo's laws. Galileo extrapolated simple observations on motion of bodies on inclined planes and arrived at the law of inertia. Newton's first law of motion is the same law, rephrased, thus every body continues to be in its state of rest or of uniform motion in a straight line unless compelled by some external force to act otherwise. In simple terms, the first law is if external force on the body is zero, its acceleration is zero. Momentum of a body is a product of its mass and velocity, P equals mv. Newton's second law of motion, the rate of change of momentum of a body is proportional to the applied force and takes place in the direction which the force acts. Thus, force equals k dp by dt, which we can write it as k times mass into acceleration, where the proportionality constant is 1. So we directly write it as force equals mass into acceleration, where F is the net external force on the body and A is its acceleration. We set the constant of proportionality k equals 0 in SI units. Then force equals dp by dt and force equals mass into acceleration. The SI unit of force is 1 Newton. 1 Newton is 1 kg per meter, 1 kg meter per second square. The second law is consistent with this first law, where force equals 0 implies A equals 0. It is a vector equation. It is applicable to a particle and also to a body or system of particles, provided F is the total external force on the system and A is the acceleration of the system as a whole. F at a point at a certain instant determines A at the same point at that instant. This is the second law. It is a local law. A acceleration at an instant does not depend on the history of motion. At that motion, it will not remember. There was an example given about a train. When we throw a rock, or like when we are throwing a ball or a rock outside an accelerating train, at one moment when we are holding the ball or the rock, the along with the train, we along with us and along with the train, the rock or the ball will also be accelerating. But the next moment when you throw it outside, it does not remember that it is accelerating, and the instant it is out of our hands, it stops accelerating. That is what they mean. It does not depend on the history of motion. Impulse is the product of force and time, which equals change in momentum. The notion of impulse is useful when a large force acts for a short time to produce a measurable change in momentum. Since the time of action of the net force is very short, one can assume that there is no appropriate change in position of the body during the action of an impulsive force. This is a very important statement. Let's read that again. Impulse is a product of force and time, which is equal to the change in momentum. The notion of impulse is useful when large force acts at a short period of time to produce a measurable change in momentum. Since the time of action of the force is very short, one can assume that there is no appropriate change in position of the body during the action of the impulsive force. This line, the last line, since time of action of the force is very short, one can assume that there is no appropriate the distance where the displacement of the body is very less, but the change in momentum is great. There is a great change in momentum, but change in displacement or change in distance, which is basically displacement, is not very high. Newton's third law of motion: to every action there is always an equal and opposite reaction. In simple terms, the law can be stated thus: forces in nature always occurs in pairs of bodies. Force on a body A by body B is equal and opposite to the force on body B by A. Action and reaction forces are simultaneous forces. There is no cause and effect relation between action and relation, meaning it does not depend like first action happens and second reaction comes. That is not the case. Both happen at the same time, at the same instant, meaning no matter if it is a force on A due to B or force on B due to A, we can call it as action or we can call it as reaction. It depends on us. Any of the two mutual forces can be called action and the other reaction. Action and the reaction act on different bodies and so they cannot be cancelled out. We cannot say that the forces are equal and opposite, so we cannot say the net force on the two bodies is zero. We cannot say that. If it was on a single body, we do not consider itself as a third law. And if two equal and opposite forces are acting on a single body, it is not the third law, and at that time the net force on the body is zero. But here when it is acting on two different bodies, it is not zero. The total net force is not zero. The internal action and reaction forces between different parts of a body do, however, sum up to zero. When we consider the whole system, when we consider the system, when we consider two different bodies, and we consider these two different bodies to be a single system, then the single system will have a net force of zero, or a net force like a law of conservation of momentum. Momentum is conserved, like, yeah, different between parts of the same system. Law of conservation of momentum. The total momentum of an isolated system of particles, it is conserved. The law follows from the second and third law of motion. Okay, and frictional force opposes the impending or actual relative motion. between two surfaces in contact. It is a component of the contact force along the common tangent in surface in contact. It is found experimentally that I think I was not audible. I was not sure. I'm not sure how much time I was not audible, but okay, let's start from point 7. Law of conservation of momentum. The total momentum and isolated system of particles is conserved. The law follows from the second and third law of motion. Friction, frictional force, opposes the impending or actual relative motion between two surfaces in contact is the component of the contact force along the common surfaces in contact. Tangent common surfaces in tangent to the surface in contact. Static friction Fs opposes impending relative motion. Kinetic friction Fk opposes the actual. Okay, let's continue. Law of conservation of momentum. The total momentum of an isolated system of particles is conserved. The law of The law follows from the second and third law of motion. Frictional force opposes the impending or actual relative motion between two surfaces in contact. It is a component of contact force along the common tangent to the surface in contact. Static friction Fs opposes the impending relative motion. Kinetic friction Fs opposes the actual relative motion. They are independent of area contact and satisfying the following approximate laws. Mu s coefficient of static friction and mu k coefficient of kinetic friction are constant characteristics of the pair of surfaces in contact. It is found experimentally that mu s is less than, mu k is less than mu s, and mu r rolling friction is even less than both of them. These are the specific quantities they gave. Let's see. Momentum, denoted by P, units is kg meter per second or Newton per second. Newton second. Dimensions is mlt power minus 1. It is a vector. Force F, units is Newton, mlt power minus 2. Dimensional formula, F equals mass into acceleration. Impulse, kg meter per second or Newton second, and mlt power minus 1. Impulse equals force into time, or it is change in momentum. Static friction, Fs, which is units is Newton of course, and which is it's basically a force, and mlt power minus 2. The formula is this one. And kinetic friction, it is denoted by Fk. Newton is a symbol, unit. mlt power minus 2, same dimensional formula as force. The formula is mu s times normal force. They gave points to be pondered. Let's read that as well. Points to be pondered. Force is not always in the direction of motion. Okay, depending on the situation, force may be along the velocity, opposite to the velocity, normal to the velocity, or may make some other angle with velocity. In every case, it is parallel to the acceleration. Where all these cases we see when it is force is not always in the direction of motion. Motion is the direction where velocity is happening. Velocity is the direction of motion. But when if it is acceleration, during the time of acceleration, it might be when if the particle is in rest, or when we are pushing the object, applying force on the object in the same direction as its velocity, then both the velocity direction and the motion of the body and the force and acceleration will also be in the same direction. But what if the body was decelerating? Then the acceleration will be opposite to the velocity component. What if the body was already moving and opposite to it in some other angle, in some other place of the body we apply a force? Then what? It will always not be in direction of the motion. It is a point to be remembered and a point to be pondered. If velocity equals 0 at an instant, that is, your body momentarily is at rest, it does not mean that force or acceleration are necessarily 0 at that instant. For example, when a ball thrown upward reaches its maximum height, velocity equals 0, but the force continues to be its weight mg, and the acceleration is not 0 but g. Okay, when we throw a ball up, the final velocity will always be 0, and when it reaches a certain height, at that time we know that the acceleration will always be acting towards the earth. The force also, the gravity as well, it is acting toward the earth, but the velocity is 0. The ball or any kind of stone is not moving at that height. That is the second point. Force on a body at a given time is determined by the situation and the location of the body at that time. Force on a body at a given time. This force on a body at given time, this is determined by the situation at the location of the body at that time. Okay, force is not carried by the body from its earlier history of motion. The force is not carried by body from its earlier history of motion. The momentum after a stone is released from an accelerated train. There is no horizontal force or acceleration on the stone. If the effects of the surrounding air are neglected, the stone there has only a vertical force of gravity. Okay, they're saying this is the example we talked about before, just a few minutes before, where I said when there is no history, it doesn't remember the history that it was in acceleration. It will not remember the history of acceleration when it is out of the range of acceleration. The moment it is out of the train, it is out of our hands. It is not accelerating. It is not experiencing any kind of force. The only force it is experiencing in case of the stone we throw out of an accelerating train is, if we do not consider air resistant, it is only gravity. In the second law of motion, force equals mass into acceleration. F stands for the net force due to all material agencies external to the body. A is the effect of the force. Mass acceleration should not be regarded as yet another force beside F. Okay, if the second law of motion, which is force equals mass into acceleration. Force stands for the net force due to all material agencies external to the body. The force, which is F denoted by F, stands for all the net force, the total force on a body. The total net force on the body is the F. And here, due to the force, the effect of that force is acceleration. Just like how in circular motion, the effect of centrifugal force is a circular motion. The effect of the force here is the acceleration. Acceleration is the effect of force, and mass into acceleration should not be regarded as yet another force besides F. F is the one that is mass into acceleration. Mass into acceleration is not another force. It is just denoted, or we can calculate force by mass into acceleration, or we can approximate the total net force on the body through through the product of the mass and acceleration. The centripetal force should not be regarded as yet another kind of force. It is simply a name given to the force that provides inward radial acceleration to a body in a circular motion. Yes, circular centripetal force is not any other kind of force, but it is a force which is just acting towards the center of the body, I mean center of the circle, and it's providing a circular motion to the particle, that is a particle or a body. We should always look for some material force like tension, gravitational force, electrical force, friction, etc. as the centripetal force in any kind of circular motion. Okay, any kind of these forces will provide a circular motion. So they are called as centripetal forces. Static friction is a self-adjusting force up to its limits, where mu s times n for static friction is less than mu s times n. Do not put Fs equals to mu s times n without being sure that the maximum value of static friction is coming into play, because we know that depending on the static friction is varying depending on how much force that is getting applied. There is a limit. As the force increases, the static frictional force also increases up to a certain limit. So that is why we keep an inequality sign here. Unless we know that the static friction is at its maximum, we should not put the static friction to be equal to mu s times n. The familiar equation mg equals r for a body on a table is true only if the body is in equilibrium. Okay, because mg equals the normal force, they're saying this only is true if the body is in equilibrium. But what if the body was in undergoing acceleration? If the body was in acceleration, then the resultant force will also change. It can only This is only true if the body is in equilibrium, where we saw before in the soft body, the soft floor. Example, the two forces mg and r can be different. Example, a body in an accelerated lift. In an accelerated drift, the actual values of n and mg will be different. The equality of mg and r has no connection with the third law. This equality has nothing to do with the third law. It only states that the net force experienced by a body due to another body is equal and opposite to the body B by body A. The terms action and reaction in the third law of motion simply stand for simultaneous mutual forces between pair of bodies. Unlike their meaning in ordinary language, action does not precede or cause reaction. Action and reaction act on different bodies. The different terms like friction, normal reaction, and tension, air resistance, viscous drag, thrust, buoyancy, weight, centripetal force all stand for force in different contexts. All are force itself, but they are just different kinds of forces we see in nature. For clarity, every force and its equivalent terms encountered in mechanics should be reduced to the phrase force on A by B. They can all be reduced to the terms force on A by B in case of tension, air resistance, viscous drag, or thrust or buoyancy, all of them. For applying the second law of motion, there is no conceptual distinction between inanimate and animate objects. For applying the second law of motion, we don't need any conceptual distinction between inanimate and animate objects. A moving and a non-moving object, we don't need any kind of distinction between that. Basically, animate and inanimate meaning. An inanimate meaning are a body in rest. Animate meaning a body that is moving. An animate object such as humans also requires an external force to accelerate. For example, without the external force of friction. Wait. I believe animate and inanimate don't refer to moving and not moving things, but living and non-living things. That might also be the case. Force equals mass into acceleration, not only for non-living things, but even for living things as well. As an example, external force of friction, we cannot walk on the ground or floor. The objective concept of force in physics should not be confused with the subjective concept of the feeling of force. On a merry-go-round, all parts of our body are subject to an inward force, but we have a feeling of pushed outward in the direction of impending motion. Basically, a merry-go-round is basically like uh, a circus, where not a circus, but basically we are rotated in a circular motion in such a way we feel that we are feeling a force outward, we are pushed outward in the outward direction, but the force is actually acting inwardly. And this is not to be confused, where feeling of force should not be confused. With that, I have completed first revision of laws of motion completed. Okay, then see you guys in my next video. Good night.